This tiny brain powering your computer? It started as rock. Today, we're going to travel from sand to silicon and watch a CPU come to life step by step. Before we start, drop a guess. How many transistors are on a modern CPU? Millions, billions, or trillions? Hold that answer. Silicon is a semiconductor, sometimes a conductor, sometimes an insulator perfect, or building on-off switches we call transistors. And yes, it's ultimately sourced from sand, rich in silicon dioxide. We begin by purifying silicon from quartz into electronic-grade silicon. This isn't ordinary sand. It's refined until impurities are measured in parts per billion. Why? Because even a trace of iron or calcium can ruin the delicate electrical properties we rely on. Next, we grow a flawless single crystalline ingot using the Czochralski process. A seed crystal is dipped into molten silicon and slowly pulled upward while rotating. Atom by atom, the crystal lattice aligns, forming a cylinder that can weigh hundreds of kilograms. Pop quiz. Why do we need a single crystal? A looks cool B prevents electron scattering and defects C, easier to cut. Answer in chat reveal in 10 seconds. The answer is B. Defects kill performance and yield. Once the ingot is ready, we slice it into thin wafers, each only a fraction of a millimeter thick. These wafers are polished until they reflect like mirrors. Even nanoscale bumps would distort the microscopic patterns we're about to print. Now, imagine the environment where this happens. Dust is a killer. One stray particle can short 2 lines or block a via. That's why chip making happens in ultra-clean rooms, where workers wear full-body suits and air is filtered constantly. Interactive moment. Picture painting an entire city on a coin. Now imagine a dust speck the size of a car landing midstream. That's what a single particle looks like. The features measured in nanometers. With wafers prepared, we begin the real magic, building the CPU in layers. Each cycle follows a rhythm deposit, pattern, etch, and go. Photolithography is the master stencil guiding this dance. First, we grow or deposit thin film silicon dioxide or high-Chi dielectrics that insulate parts of the device. Think of them as walls in our microscopic city. We then spin coat photoresist, a light-sensitive polymer. Using a mask in extreme ultraviolet light, we expose patterns. Where light hits, chemistry changes. After exposure, we develop the resist, washing away selected parts, then etch the underlying film where it's unprotected. The resist is our temporary stencil, guiding the sculpting of nanoscale features. To make transistors switch, we dope regions with atoms like boron or phosphorus. These donors and acceptors set up N-type and P-type regions. Ion implantation fires ions like microscopic bullets into silicon, precisely controlling concentration and depth. We deposit more materials, polysilicon gates, metal gates, nitrides, oxides, then use chemical mechanical planarization to flatten each layer. Flatness matters. Without it, the next layer's patterns won't align. Quick quiz. What makes a transistor a switch? A. Magnetic fields. B. Changing the gate's electric field. C. Heat flow. The answer is B. The gate voltage modulates a channel's conductivity. Transistors are the neurons, but interconnects are the synapses. We stack multiple metal layers, often copper, with tiny vias connecting them vertically. To keep signals clean, we add low-K dielectrics between lines to reduce capacitive coupling. And nanoscales. Wires resist and capacitors load signals. Designers balance wire length, width, and repeaters to meet time. Clock networks distribute timing with astonishing precision. Picoseconds matter. Analogy. Imagine a 50-story city with roads on every floor and elevators between them. Now drive every car to the right place at the right time. That's the job of interconnects and clocking. Before cutting the wafer, Tiny test needles probe each die to check basic functionality. Not every die survives defects. Yield determines how many chips we ship. We saw the wafer into dies, then mount each die onto a package that protects it and connects to the outside, rolled through micro bumps, wire bonds, or flip chip solder balls. Underfill and thermal interfaces help manage heat. The heat spreader and cooler carry it away after assembly. Chips undergo more tests and are binned, sorted by max stable frequency, power, and features. That's why two CPUs with the same design can ship at different speeds. Viewer poll. Pick one. If two chips are identical except max clock, would you pay more for higher frequency or prefer lower power? Inside the chip, billions of transistors compose logic gates, ALICE, caches, and cores. Caches sit close to the cores to feed data fast. Branch predictors guess what you'll do next. Parallel cores and simultaneous multi-threading keep the silicon busy. A CPU decodes instructions, schedules them across pipelines, and retires results in order while the microarchitecture juggles hazards, speculation, and memory latency. Clock ticks slice time into billions of tiny moments, where electrons race and stop like interactive thought experiment. Open your system monitor. Watch CPU usage spike when you compile code or render video. Each spike is billions of transistors flipping in lockstep. We started with sand. Purified silicon grew perfect crystals, sliced wafers, and built devices layer by layer etching. Doping, wiring, then tested and packaged the die. That is how a CPU is born. And the transistor count? Modern high-end CPUs pack tens of billions of transistors. From grains of sand to seas of switches dot. Comment with the step that surprised you most. Want a deeper dive on photolithography?